The main topic this week is centering. And you've learned about what centering can do for interpretation in normal single level regression, but it has a few extra nice properties for hierarchical models that are important to think about. So we've talked about in your lecture two different techniques for centering in hierarchical models, grand mean centering and centering within cluster. So just take a second to try to refresh yourself on why and when we'd want to use these techniques and how these different techniques influence our parameters and their interpretations. Centering in R is fairly straightforward. So for grand mean centering, we can either simply subtract a variable's mean if we're doing one variable at a time, or we can use the scale function, which is a little bit more flexible. And then all we have to do is set the scale argument in the scale function. Yes, the scale function is a scale argument. And we want to set it to false because what that does is it says that we don't want to also divide by the standard deviation, which would fully standardize our variable. For centering within cluster, we start similar to building our contextual effects model, but then we subtract the variable by its cluster mean instead of just using it as a predictor. So here's some code where you can see how we would do the centering. Here you see the scale function simply is calling scale on the variable that we want and then setting scale equals false. The one thing about this is that it will add some attributes to your variable, which may make it a little bit funky to do some other things with, but don't worry about that too much for now. For centering within cluster, we start by getting our cluster means the same way we would with the contextual effects models. The only additional step is we then subtract the cluster mean from the variable itself. So to think about what the difference between these two techniques is, let's try an experiment and let's try to anticipate what the result of this experiment is going to be. If we use a centered within cluster variable as an outcome in an unconditional model, what do we think the results are going to look like? Specifically, what's the variance of the intercepts going to be? And what's the interclass correlation going to be? So here we fit our unconditional model with a centered within cluster variable as our outcome. And so it's an unconditional model again because it only has the cluster means as the predictor. And we print the variances, and what we see is the cluster mean variance is basically zero. This is just a rounding error. It should be zero. It's so small as to not even be meaningfully interpretable. And so the ICC is also zero. And what this tells us is by centering within cluster, what we've done is we removed the variable's level 2 variability. Now it only has level 1 variability. So we're going to look at some examples, or we're going to talk about the theoretical interpretations with random intercepts models, just because they're a little bit easier to understand. But most of this is going to also apply to random slopes models. It just won't be specifically as precisely as applicable, but the general interpretations also still apply. So for grand mean centering, we can do this with both level 1 and level 2 variables. You can center a level 2 variable at the grand mean, and you can center a level 1 variable at its grand mean. And this preserves the level 2 effect of level 1 variables. Really all you're doing is you're moving the center of the variable, but you're keeping everything else the same. In a model without contextual effects for a level 1 predictor, that means that the fixed level 1 predictor, the fixed effect, is going to retain its ambiguity at level 1 and level 2. In a contextual effects model, when a level 1 variable is grand mean centered, the gamma 0, 1, the level 1 effect, becomes the within cluster effect, and the gamma 0, 1, the level 2 effect, becomes the contextual effect, which is the difference between the level 1 and level 2 effect. When you do centering within cluster, this really only applies to level 1 variables. You can't center a level 2 variable at its cluster mean because the cluster mean is consistent. It wouldn't actually change the level 2 variable. Centering within cluster separates level 2 effects from level 1 effects. So in a model without contextual effects, a level 1 predictor loses its ambiguity and it becomes a within only effect. In a contextual effects model, when a level 1 variable is centered within cluster, the gamma 0, 1, the level 1 effect, remains within cluster effect. It doesn't change. as a result of adding the level 2 predictor. And the level 2 predictor, the contextual effect, becomes pure or total between cluster effect. So the idea is that we're actually separating out the correlation between the within and the between. That way we can capture the between separate from the within. Let's take a look at what this looks like in actual practice. So we're going to start by fitting a grand mean centered model without contextual effects. And what we see is these results are very similar to what we saw when we looked before. When we looked last week, the level 1 predictor is the same as what we saw, and the intercept is the same. Now, when we add the contextual effect, again, we see now these results are the same as what we saw last week. This is our contextual effect. This is our level 1 effect. But the intercept is a little bit different because we've centered. Now, pay attention to, in particular, the level 1 effect as we look at centering within cluster. So now that we center within cluster, we look at a model with only a level 1 predictor. We see that the level 1 effect is the same as it was in our contextual effects model for grand mean center. So that's because we've totally separated out the within cluster effect from the between cluster effect. And this is only a within cluster effect. There's no ambiguity here. When we add now the cluster means, we see that the within cluster effect stays the same. And this is now a pure between cluster effect. And when we compare this to the version with grand mean center, this is a contextual effect. So this is the difference between the level 1 and level 2 effect. And this is the pure level 2 effect. Conceptually, everything is pretty similar when we have random slopes, but because the slopes also vary, the fixed effects will change a little bit more between models. So the reason I wanted to illustrate with random intercepts models is because those numbers stay exactly the same. They wouldn't stay exactly the same with random slopes models because things would change as a result of varying slopes. Centering is also important for random slopes, though, for another reason, and that's due to the correlation between random effects. So let's take a look at 3 different random slopes models: uncentered, grand mean centered, and centered within cluster. So we're going to look at the random effects results, and in particular, you should try to pay attention to this first row, which is the residual for the random intercepts, and this row here, which is the correlation or covariance between the random intercepts and random slopes. And we can look at the standard deviation and the correlation just for ease of interpretation here. So we see the standard deviation of the intercepts after accounting for the predictors is 1.31. And we see the correlation between the intercepts and slopes is negative 0.46. This is, again, very similar to what we saw last week. This is exactly what we saw last week when we looked at the uncentered model. Now, when we center at the grand mean, we see that both of these parameters have reduced considerably. So the correlation is now very, very small. And the variance in the intercepts has also decreased. When we look at the center within cluster version, the correlation is a little bit bigger, but still small, as is the variance in the standard deviation in the intercepts. So what's going on? Why is the standard deviation of the intercepts and the correlation between intercept and slope tied together like this? And a good way to understand what's happening is to visualize it with the spaghetti plots, like we did last week. So first we'll look at the uncentered spaghetti plot, and this is the same plot again that we looked at last week. So we see again that's the same plot that we saw with the random slopes for different participants for the same 40 participants that we saw last week. And again, this is the uncentered model. Now let's look at the grand mean centered model. In addition to using the different variable, grand mean center sleep, I'm also changing the x-axis, so it goes from the minimum to the maximum of the grand mean centered sleep. This is the same thing as we were looking at in the other version. It's just that the minimum and maximum are different. They're no longer integers, so I just specified them as the minimum and the maximum. And then the other thing I'm going to do is I'm going to add a vertical line at 0 because the x-axis in this model is no longer going to go from 0 to 9. It's going to go from a negative number to a positive number. And I want to be able to visualize the actual x-intercept. So I'm drawing a vertical line with geom v line with x-intercept equals 0, so we can visualize that. And this is what it looks like. So we see we have a vertical line here at 0. This is our intercepts. Before, our intercepts were over here, and you can see that there's much more variability in these intercepts. And here there's much less variability in the intercepts because they're all bunched together in the middle. We can do the same thing with center within cluster. And again, I'm doing the same thing. I'm ranging the x-axis from the minimum to the maximum, and I'm drawing an intercept at 0. And so the data points are a little bit messier looking here because we centered them within cluster, but the idea is the same. Now our intercepts are all a little tighter together because we've centered the data rather than having it at its extreme where the intercept would have been all the way over here, and so there would have been much more variability. So the idea of what's going on here is that if you set your intercept at the extreme tail of your theoretical distribution, and this is assuming a continuous and symmetric distribution in a random slopes model, the cluster-specific intercepts are going to get further apart. So if your distribution, theoretically, if 0 is in the tail of your distribution, then the intercepts are going to be very far apart because that's the value when the predictor is 0. Additionally, the correlations between slopes and intercepts will increase when you're in the tail. And that's because steeper slopes means more extreme intercepts. So if you center, you're bringing everything more towards the middle. So you're both reducing the variability in your intercepts and you're reducing the correlation between your intercepts and your slopes. So centering is often going to help with this. It's not guaranteed to help in the case of ceiling and floor effects, for example, among other possibilities. But in general, this is an advantage that centering has, is that it reduces the variability in our intercepts and it reduces the correlation between our random intercepts and random slopes.